Okay, so I think that what we'll do is I'm going to write this stuff out a bit. Can everyone see the little my window for notebook or OneLook or OneNote? Okay, super. So when we're talking about proton NMR, there are essentially four things that we're going to be looking for. The first is the number of signals. And this is going to represent how many different kinds of protons are present. We'll go into in detail for all of these things. The second thing which we're going to be looking for is the position of the signals. Because this is going to tell us basically the electronic environment. What else? 3. The intensity. Of the signal. This is going to tell us the number of protons the number of protons that are basically used to make that signals. Number of protons, let's say, represented by that signal. And the fourth thing, which we haven't seen yet in any of the things, in any of the spectra, is the splitting of the signal. And this is going to tell us about the environment with regard to how many protons are nearby. So this is going to tell us the number of protons close to the proton that generated the signal. So this is going to tell us the not necessarily the electronic environment, but the proton environment, like the number of protons that are nearby. So there's basically four things: the number of signals, the position where they happen to be, the intensity of them, and are they split or are they just a signal, simple single signal. How's that? Okay, so let's look at the number here. Okay, so let's see here. Protons with the same environment. That's an M and an N together. Okay, so think of this as protons that are equivalent in chemical reactions. So protons with the same environment, so they're equivalent in chemical reactions, are said to be equivalent. So these would be chemically equivalent. So, and they should resonate at the same field strength. So, so they should. So what's a good example? So if I've got, stop that, C3, so methyl chloride. There is, or there are 3 different protons here, right? So we got, let's draw them. So carbon's tetrahedral, there's 3 protons there. My question is, are these 3 protons chemically equivalent? If you were to say deprotonate this compound with a base, would one of those 3 protons be more susceptible to be removed, or would all 3 of them have an equal chance? They are indeed equal. So these 3 are all equal. So we should see, basically, if we run an NMR of this, we should see 1 signal for these 3 protons, because all 3 of them are chemically equivalent. Now, if we have, say, ethyl chloride, how many different signals should we see here? 2, right. So we've got 2 protons that are on a carbon directly attached to a chlorine, and we've got 3 protons on a carbon, which is 2, which has got a carbon in between. So here we should indeed see 2 signals. So I'll call these 2 here A, and I'll call these 3 here B. And let's just take this 1 step further. How many signals should we see in a situation like this? Right, 3. So I will number these A, just B, and C. So we should see 3 signals. Alrighty, where's a couple more examples? How about how many different protons do we have here?
Three.
We have got
Actually, no, two.
2, right. Okay, so these 3 here, A, would be the same as these 3 here, A, and this proton here, B, would be by itself. So, right, so we would have 2 signals in this case. All right, let's do this. How many different signals should we have in a cyclohexane? One. Okay, so if you look at this purely from a yes, so this would be one signal. There's a caveat to this, that being that a cyclohexane is a chair. And if you cool it down at a low enough temperature, you can actually distinguish between the axial and the equatorial protons. But for what we're doing, a room temperature, right, there would be one signal. All of these would be equivalent. So I guess a better example would be, where you don't have to worry about chair conformations, would be if we had benzene. So benzene, all of the protons are equivalent, so we would have one signal. Let's do a slightly more complex example. How about this? How many different protons signals should we see here?
I guess 3, since I think whether or not the hydrogen's on the same side as the bromine might make a difference.
Okay, so we got 3. Yes, so to be chemically equivalent, protons also have to be what we would call stereoelectronically, stereochemically equivalent. So we've got, I'm going to label all these protons different things here. So let's call this one, these HA, HB, and HC. So proton C is cis to this bromine. Proton B is trans to the bromine. And then proton B is cis to the methyl group. And proton C is trans to the methyl group. So protons B and C would not be equivalent in this case, because they've got their spatial arrangement is being cis and trans. So so these would be inequivalent. So you should see 3 signals for this in this case here. Now, this is the maximum number that you should see. One of the things that when we're talking about the energy gap between the two, like the spin up and the spin aligned and the spin opposed nuclei, when you put it in the magnetic field, that energy difference, the larger that energy difference, the bigger the resolution would be between the chemical shifts of, say, HB and HC. So with a 60 megahertz machine, these two might come out, B and C might come out at the same parts per million. But on a 400 megahertz machine, they would be distinct. They could be distinct signals. So it's one of the things that when you're looking at a low resolution machine, sometimes protons that aren't actually equivalent come out at the same resonance, because because that energy gap isn't quite large enough. Now, if we had if we were to replace this bromine with a methyl group, then we should see two signals, right? So if we had, so CH3, H. Here, we should see the same, there's a plane of symmetry right in between the carbon-carbon double bonds. So each proton is cis to a methyl group and trans to a methyl group. So there's, you should see two signals there. This gets, yeah. Now, one of the interesting things for those of you who just took, where we just did stereochemistry in the organic class, if we've got two enantiomers here, let's just draw it like this. So how many different signals should we see in the spectra for, say, this compound on the left? How many different protons are there? I've got a guess of 3. Anybody else? 5? Okay, let's take a look here. So, what color should we use? We will use blue. Okay, so there's 3 protons here. We'll label them 1. There's 1 proton on this carbon, 2, 3, 4, and then the proton here on this oxygen, 5. So we could see a grand total of 5 different signals for this, for 2-butanol. Now you notice that there's an enantiomer of this compound where this OH is going into the background. So the thing about NMR is that NMR can't be used to distinguish enantiomers. Unless there is actually a technique called there's a Mosher ester technique where you convert your alcohols to esters, and there's a really neat little way of doing it with fluorine NMR. But if you've just got a mixture of 2 enantiomers and you run a standard proton NMR of it, they will both have exactly the same spectrum. So that's one of the interesting things, is that so 2 enantiomers in a bottle, like if you got a bottle of plus minus, I don't know, the 2 enantiomers will have the same proton NMR, unless you're doing a special experiment, which includes using a chiral solvent or a chiral derivatizing agent. But for a simple proton NMR, you can't be used to distinguish enantiomers. The organic class hasn't found out what a diastereomer is. But for those of you who have taken organic before, what's the definition of a diastereomer with regards to stereoisomers? So stereoisomers that are not mirror images and are not superimposable. So an enantiomer, remember, is a mirror image, non-superimposable. A diastereomer is, they're not mirror images and they're not superimposable. So cis-trans diastereomers, these are not mirror images of one another and they are not superimposable. Now, when you're talking about carbons that have got sp3 hybridized carbons, the most common source of diastereomers is that if you've got two chiral centers, so say OH, 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 OH. So the enantiomer of this guy would of course be this. So the two chiral centers are reversed. Oh, this is probably a bad example. Let's put a extra carbon here. Let's put an extra carbon there. So the enantiomer of the two chiral centers would be reversed, so wedges. But a diastereomer, one chiral center would be the same. So these guys here are the same. And one would be opposite, right? These are opposite, right? So diastereomer has got one chiral center the same, one chiral center opposite or more. So that means that they're non-mirror images and they're not superimposable. Proton NMR can distinguish between diastereomers. So with enantiomers, the NMR spectra will look the same, but with diastereomers, they can be quite different. So that's one of the interesting points to this. So as I said before, like if you can just look at the structure and you can say to yourself, well, we should have X number of signals. That's the maximum. And depending upon the field strength of the spectrometer, sometimes two protons that you would view as being chemically unequivalent, they might have a coincidental resonance at a low field strength. But if you were to increase the field strength enough, you should be able to separate them out into two different distinct signals. Okay, is everyone happy with that? If we were to draw a structure to be able to theoretically pick out how many different signals we should see? Okay, then let's move on to the next part, the position of the signals. So this is going to tell us the electronic environment. So I went on to Moodle and I just checked to make sure that the NMR correlation chart was there. It is there, and you should be able to like pick it up and look at it. Maybe I can. I don't have it handy. Okay, so I'll go through that in a second. Okay, so let's actually share the PowerPoint. I think the position of the signals is better with the PowerPoint. All right. We'll come back to these ones here in a second. Okay, so this is basically the correlation table for proton NMR. This is a really simple one. There's a better one on Moodle in the appendices. So I guess there's four regions that we'll look at. The first region occurs above 9 ppm. And there's really essentially two types of protons that you will see up there. That being the aldehyde proton and the carboxylic acid proton. So they're in a really de-shielded zone. And in the case of the aldehyde, it's because of the influence of the carbonyl group. With regard to the carboxylic acid, there's two things. It's the influence of the carbonyl group plus the electron withdrawing nature of that oxygen. So if you see a peak above 9, it's typically either an aldehyde or a carboxylic acid. One of the things that we'll get to later on is that, and it's actually up here at the top of the spectra, OHs and NHs. You'll notice that it's a very, very, very broad range. Protons attached to heteroatoms tend to have the signal really, the position of the signal is often solvent dependent, and it's often concentration dependent as well. So they're not particularly reliable. And instead of being a nice little sharp peak, they tend to be blobs. So you can often tell if a peak is, if a proton's bonded to a heteroatom like nitrogen or oxygen specifically, if it comes out as sort of a blobby shape. So a carboxylic acid up in this zone will be sort of, for lack of a better word, a blob. And an aldehyde would typically be a sharper peak. But we'll get into why heteroatoms have got this wide range a bit later on in the class. The second zone, so I'll call this zone 1. The second zone is approximately around 6.5 or so to 8.5. If I can change the color of this. I'll go down to 5. And this is in a region where you're going to find your aromatics and alkenes. Some of them go below here. That's really special circumstances. So this is where you're going to find these types of, these protons are de-shielded significantly. That's why they're down here. Another proton that is de-shielded around 7 is chloroform. And so when you run your NMR spectra in deuterated chloroform, so CdCl3, the bottle usually is something like 99.9% deuterated chloroform. The other 0.1% is chloroform. So there's a little tiny bit of chloroform in there. And this signal comes in at around 7.2. And in the Fourier transform spectrometers, rather than putting in a reference at TMS, they typically, the reference is actually the residual chloroform coming out at 7.2. So they place the other resonances based upon that as opposed to TMS, just because there's a residual peak. And so when the spectrometer goes through the process of locking on the sample, which is something it has to do, locking on a frequency, it's locking on the residual chloroform peak. And so everything will be in relation to that. So this is zone 2, where you've got the aromatics and alkenes. And we'll explain why they are a de-shielded type of in a de-shielded zone. Now the next bit is between, say, 2 and 5. So in this region, you see most of the other interesting functional groups. So protons that are near fluorines or chlorines or bromines or iodines, or close to oxygen, or protons that are near an aromatic ring or a carbonyl, all of them come in this sort of zone here. So this is an interesting place to look. And then 2 to 0, these are basically alkanes. So the backbone of the whatever your molecule happens to be. So if we had, for example, this molecule here, how many different signals should we have for it? Well, ignoring the fact that it could be a quasi-chair or whatever, but just what would be the theoretical maximum number of different protons that we should see? I've got one guess at saying 3. Anybody else? 7? Okay, let's count. What would be the maximum number here? Okay, so if we've got, okay, so this double bond isn't, so we've got a proton here, call this HA. It will be different than, it could conceivably be different than HB because this carbon is near a carbon over here with an oxygen or with a hydroxyl group. So this could be 1, this could be 2. Then there's 2 protons here, which we will call C. Then there's 2 protons here that we will call D. 2 protons here that we will call E. Because these ones would technically be different than these ones because these ones are closer to this hydroxyl group. These ones are closer to these guys over here. Then there's 1 proton here, which we'll call F, and then G. So how many is this? 1, 2, 3, 4, 5, 6, 7. Yeah, so conceivably we could have 7 different protons. The nice bit here is that of these 7, we could look specifically at ones in the different zones to, we'll call this zone 3 and zone number 4. So we could look, so we've got HA and HB, which are both attached to a double bond. So we should see 2 of these somewhere. A and B should be somewhere in the zone, in zone 2, like between 5.5 to 7 ppm, something like that. This little proton F here, it's on a carbon directly bonded to an oxygen. So you'll see here that the protons on a carbon bonded to an oxygen right here, this would be in this area here. So this would be proton F should be somewhere in the 3rd zone. You might see protons C here as well, because you notice here is a double bond down here. Or I guess I should get my laser out. Double bond, and then right next door is a carbon with 2 protons on it. So these proton C could also be found in this zone here. And then we'd have D and E would probably be somewhere, D and E would probably be down in the most shielded area. The hydroxyl proton, that's going to be a blob, so we should be able to notice that one by itself anyway. So when it comes to an analysis, we could immediately look to see, do we have protons A and B in this area? Do we have protons C and F in the middle area? And then finally, the remaining ones up close to 0 ppm. So that's basically how I tend to tackle, particularly if you know what you're making, right? I'm trying to make molecule A, and I started with molecules B and C. I would look in, like, I know what the structure I'm looking for. Let's look for evidence of the protons in the various areas where they should be. So that's how we do this. Now, you'll notice that in zone 3, where you've got the fluorine, the chlorine, the bromine, the iodine, and the oxygens, and the nitro groups, and all these sort of things, there's a wide variety of parts per million where this can take place over. So in the appendices of the correlation tables, it actually goes into detail on if you've got a CH, which is attached to a carbon with a bromine, or a CH2 or a CH3, and it gives you a more defined area of where you should find those protons. So it's actually quite helpful. So on Tuesday, we're going to do some analysis of some spectra, and it should become, with practice, it'll become second nature. Okay, so the next slide here, where is it? Stop that. So now, when we had our, let's erase this stuff. So remember when we had our little proton, and it caused the electrons to circulate around it because it was, and then that induced a magnetic field. So induced, and then it induced a magnetic field that was opposed to the applied field. So the induced field was pointing down and the applied field was pointing up. So if you had in a shielded like in a saturated, when the carbon's surrounded by silicons and other carbon stuff, these are shielded and they're down near 1 to 2 ppm. Now with the aromatic rings from the previous slide, aromatics were way up here at around 7 and 8, and the double bonds were near 6. Something entirely different is going on here. So what's happening is that you've got the electrons are circulating around the ring, and this is generating the same field, which is opposed, overall, this is opposed to the applied field. But the location of our little friends, the protons here on the aromatic ring, they're in an area where this induced field is now aligned with the magnetic field. So the little protons on this ring here, which are pointing out, they're now in these circulating electrons, the pi electrons that are circulating around, they're in a zone where now this induced field is aligned with the applied field. So this makes them very de-shielded. So that's why they're down at 7 ppm. So aromatic rings, a lot of the protons are around 7 ppm. So that's why the little guys are sticking out, and they're in the zone of this applied field where it's now aligned with this induced field. They're in a zone which is aligned with the applied field. So that's why they resonate at 7 ppm. And for carbonyls, I don't know if I've got an example of this. I sort of do. Um, erase this stuff. Please let me erase it. So what these diagrams here are basically showing is that the negative parts are zones of de-shielding. So negative equals de-shielding. So this is high ppm. And the positive parts are shielded. So this is low ppm. And so with the carboxylic acid or an aldehyde, these are right in the negative zones. So this would be de-shielded. So with and same thing with double bonds, they're in the de-shielded zone. Now the difference between an aldehyde and a double bond is that you've also got there's electronegativity differences which are also de-shielding it. So that's why this is greater than 9 ppm. Now the one example which is slightly different is with triple bonds. The protons actually are in a shielding zone, so they come out at around 2 to 3 ppm because the electrons are circulating here and then or they're circulating around this way, and so they're in the they're circulating this direction, so they're in a zone of high shielding. So if you were to, which is interesting, and people have done this, so you'll notice that the regions right above rings are heavily shielded. So if you were to put a proton above a ring, this should be in a shielded zone. And in fact, people have built molecules that have had a proton above this ring, and it's in that shielded zone, and it's at very, 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 very low ppms. So that's kind of neat. So they built some molecules that are either conformationally rigid, which keeps them there, or they're mobile, and you can actually watch the conformation change. That was actually oh, that reminds me. Yeah, that was when I was an undergrad, one of my honors project was on this sort of molecule. And so it's basically, I'm missing a carbon here. 2 aromatic rings that were linked with some sort of heteroatom. It was sulfur and oxygen in my case. And there's basically 2 different conformations of how these molecules could exist. One is sort of like a sandwich. And one is like a step, so to speak. So, and they would flip in between. You could make them rotate, flip in between. And it depended, and you could actually monitor this by checking out the chemical shift of this proton here, because this would be in a zone of de-shielding, and then as it rotated where this came around, it would now be over the ring, and it would be in a zone of de-shielding. And you could actually watch the proton migrate from high chemical shift to low chemical shift using a technique called variable temperature NMR. And you could actually get the kinetics of how these things flipped and flopped and all that sort of fun stuff. So it's interesting. Most of the other most of the other regions are based upon electronegativity differences. So chlorine or fluorine is pulling electron density away, so they will be at the higher end of this scale, whereas iodine, which is far less electronegative, would be at the lower end of this scale. So on those correlation charts, you can clearly see that, like more electronegative atoms tend to suck electron density away, and so it'll be more de-shielded. But the key points is that aldehydes and aromatic rings, they've got an induced field which de-shields these protons. So that's interesting. So the position of the signal is going to tell you about the electronic environment of the protons themselves. Okay. Oh, I didn't get as far as I was hoping. Just 2 more seconds here. So the next part was the intensity of the signals. So, oh, right. Let's go back to our PowerPoint here. Let's go back a couple slides. Right. So the intensity. Another word for what we're going to do is area under the curve. So in mathematical context, this would be integrals, right? So when you run an NMR spectra, so we've got our spectra, there's these lines here which are above the, which are basically done above the signal itself. So this is a continuous wave spectrum. And then the next one, here's a FTIR spectra. Just like in math, so an integral is basically measuring the area under the curve, and this area is basically proportional to the number of protons. So that the height of this line versus this line versus this line tells us how many protons are there. So in so this is a ratio. So if this, and in this case, the computer calculated this was basically 1.92, and this one's 2.28, and this one's here is 4.56. If you convert this into whole numbers, then this would equal 2H, this would equal approximately 3H, and this would equal 5H. And so what that's telling us is that 3 protons are responsible for this signal, which is a methyl group. 2 protons are responsible for this signal, which is a methylene group. And 5 signals are responsible, this happens to be the aromatic, and all 5 of those just happen to have the same chemical shift here. But so that's basically this area under the curve. This tells us the number of protons, 3H, 2H, 5H. So this is a ratio. So if you measure this and it's like here it goes 22, say this was 22 millimeters. So we could, and this is 33 millimeters approximately. So if this is 2, this would be 3, and this would be 5. So it's, you can put any value here, but like if this was 5, then this would be 7.5, and this would be, gosh, 2. 12.5. Gosh, so if this is given in a number, just some random number, you've got to, this represents this height, and it's a ratio between this to that to that. So keep that in mind. And the other thing which is important is this has to be a whole number, right? So you can't have half a proton generating a signal. It has to be 1. So with some, like if there were, like when you're working with this thing is, so what you could do is you could divide this by 192 and then times, so 180, sorry, 280 divided by 192, and then multiply this by 2 will give you basically 3. So it's one of those, these numbers here don't necessarily represent the number of protons. It's the ratio, it's the relation, it's because you have to make it sort of fit. So, but the ratio between here and here, because this is 3 and this is 2, this height should be 1.5 times as big as that. So if you ever come across a spectrum which has got some odd numbers, you're going to have the formula C5H10O2 or something like this. And so when you do all your integrals, those numbers should equal that number there. When we do a practice spectrum, we'll figure that out. So this is the next point, is that the area under the curve, the integral will tell you the number of protons that are responsible for this signal. So this is super, 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 super important. It's one of the aspects of the spectrum which is often forgotten, and it's one of the most informative ones. So just don't forget that. I think we're basically out of time. The last part, which I guess we'll have to do on Tuesday, is, yeah, maybe that'll set up well. The last part is the splitting of the signals. So what we're going to see is that not all of the signals just come out as one line. They come out as multiples. And that tells us about how many protons are next door. So if we do that on Tuesday, then on next Thursday, we can just do a whole bunch of practice spectra, which would be probably a good thing to do. All right, now, I basically motored through stuff pretty quick. Were there any questions? No? Okay, well then what I'll do is I will end it, and then yeah, take a look at the integrated home assignment on Moodle. It's just mass spec and a bit of infrared together. But besides that, I guess have a good weekend. And on Tuesday we'll do splitting, and then on next Thursday we'll do a whole bunch of practice spectra, just to how to work through things. Does that sound good?
Yeah.
Okay, awesome. See everybody later.
See you next week.
You bet.